Hello and welcome. This is going to be a video lecture or tutorial on some basic introductory math using Python to get you started with quantum machine learning. So maybe I should just spend a few minutes talking about what on earth quantum machine learning actually is, so that you have an idea of what you're getting yourself into, in case that sounds neat but maybe isn't your thing. So if you're not familiar with machine learning is an area of artificial intelligence where people use things like tensor networks and things like TensorFlow, PyTorch, scikit-learn, things like this to learn things. They teach machines to learn how to do certain tasks like classifying photos, and images on the internet, reading text, writing text, really interesting things like that. And it's kind of taking over the world. It's a thing, and it's becoming a very widespread, big thing. And a lot of money is being invested in startups and things like that for machine learning over the past few years. And lots of people seem very worried about things like job displacement and things like that. Some people are worried about computers taking over the world. So it's a thing. And something else that's a thing that maybe not on your radar quite as much is quantum computing. And quantum computing uses special properties of quantum physics to build specialized hardware to do a new kind of computing that's different from what you might find in your laptop or your iPhone or your iPad or tablets, whatever you're using. It's different from anything that's really being used right now. And we're going to get into some of that and explain some of the physics behind it and explain where it comes from and why it's so interesting and special and unique and what kinds of things it has to offer, especially for the machine learning community, because there are certain ways that you can use quantum computing to enhance artificial intelligence. And that's one of the things that I would like to talk about and get to. But in order to understand a lot of this stuff, on more than just a superficial level, on more than just, your 15-minute PBS YouTube video, you have to understand some math. And it's becoming more and more clear that computer programming, mathematics, and physics are all kind of becoming one thing, especially with quantum computing and with machine learning. Machine learning goes well beyond your typical programming and computer science courses. It does things that are new, that aren't just writing, for loops and things like that. It can get very mathematical. There's a very deep mathematical theory behind it. And the same goes for quantum computing too. The mathematics, I would say, is maybe as deep, maybe deeper than machine learning, especially when you get into the mixture of quantum computing and machine learning. The math can get kind of crazy. And so if you're not privy to the math, you don't know the math that's going on behind the scenes, then sometimes some of these things can get kind of confusing. Even if you're a really good computer programmer, sometimes these things can get really odd and confusing. And so you need more than just computer programming to do machine learning, and definitely to do quantum machine learning and quantum computing. So that's hopefully kind of like what I want to get at, is developing some lectures, some videos. I'm in the process of writing a book right now on quantum machine learning. And the basic prerequisites for the book are linear algebra. and a basic knowledge of linear algebra and complex numbers. And so there's actually not any, there's no programming background or knowledge required. So if you don't know how to, if you don't know how to write computer programs and you're not a programmer, you don't code on a regular basis, or you don't really have any experience with coding, that's actually okay. It's not something that's strictly required to understand the material in the book. Now, there's going to be a lot of Python used in the book to do a lot of the stuff, but it's not required that you know any Python before getting started. So a lot of the initial chapters of the book is going to be going through a lot of basic linear algebra stuff and doing this all in Python to help you get started so that you can, get your foot in the door and start understanding some of this stuff. I think what's going to be a bigger hurdle for people is not the programming, but the math, because the math can get a bit complicated. And I would say the vast majority of programmers and the vast majority of people working in just out-of-the-box, off-the-shelf machine learning probably don't know some of the deeper math that's going on behind the scenes. And in a lot of computer science degrees and a lot of people who are self-taught, linear algebra is not a course that's really required. It's something that you could take if you're getting, like an undergraduate degree or something in computer science, but it's not a course that's usually taught for computer science people. And even a lot of like physics and math undergrad students kind of dread their linear algebra course because it's very formal and mathematical, and there's lots of theorems and proofs and things like that. And it's not very computational. It doesn't end up being very hands-on a lot of times, and so it doesn't feel very intuitive. And so like that's one of the things that I'm hoping to address, because I think that's going to be the biggest hurdle for most people getting into quantum machine learning is going to be the linear algebra and some of the math behind it. And in the book that I'm writing, I'm trying really hard to make the requirements very, very minimal. And so if you do have a basic, like very like middle of the road basic understanding of linear algebra, I'm trying very hard to write the book in such a way that that is enough. You don't need any computer programming. You don't need any other mathematics or prior knowledge of machine learning or quantum physics. You don't need really anything beyond just a very basic understanding of linear algebra. So something that I'm hoping to accomplish in this video is to give some basic introductions to linear algebra using Python. And I thought maybe I would just kind of get into it and show you some examples and show you some of the choices that I've made in the book so that you can see kind of what's going on and what sort of things are going to be required. And just, write some simple basic stuff in Python to get you started with some of the linear algebra. And if some of you are kind of behind on the linear algebra, if you've never seen linear algebra, if it's something that's completely new to you, I'm going to give you some references to some video lectures that you can watch that go through a complete undergraduate level course on linear algebra, which is going to be, I would say, more than sufficient for the book that I'm writing. And so if you go through some of those video lectures and work through some examples that they cover in those video lectures, that should be more than enough preparation for the book. And the book is also going to have an entire chapter focusing on the linear algebra that's going to be needed and used constantly over and over and over throughout the book. So it's not like it's going to be just like jump right in expecting you to already know all the linear algebra. It's going to go through lots of examples in the beginning of the book to kind of get you up to speed on some of the linear algebra stuff. And also this video, I'm gonna go through some of the basic linear algebra stuff. I'm going to do it in Python. And I'm going to use something called Jupyter Lab. Jupyter Lab is one of those things where if you're not a programmer, you're not really into coding, you're not really into doing a lot of heavy-duty stuff, and you're not super experienced with using like terminal and scripting and things like that, Jupyter Lab makes everything kind of user-friendly. It kind of, it just makes it a little less stressful to get started. And I feel like is good for people who don't have a big coding background. If you do have a coding background, I know probably you're going to turn your nose up at this and you're going to be like, oh my god, Jupyter Lab, what are you doing? But it is also used a lot by people in machine learning, people who are doing data analysis, things like that. And so it's one of those things that just makes everything a little bit less stressful for people who don't have that background. So if you do have that background, awesome. You're going to have a little extra experience to get you started. But again, coding background is not strictly necessary. And I think the bigger hurdle that most people are going to have trouble with is the math. And so that's what I'm going to focus on. And I'm going to try to make the coding as painless and easy and simple as possible, and try to make it so that people who don't have a coding background don't get too stressed out trying to figure this stuff out. If you're not familiar with Jupyter Lab, I'm just going to show you where you can go download this. It's free. Everything that I'm doing is going to be completely open source and free. It's going to all be stuff that you can just download right off of the internet. There's no need to pay for anything. So if you just Google Anaconda and go to their website, this is what it looks like, and just download it up here. There's a little download button. You can download it. There's another one here. There's probably more. Who knows? But yeah, so I suggest the 3.7 version. Python 2.7 is kind of not going to be what we need. We need the newer versions of Python. But yeah, just click the download button and that'll get you started. If you go to download this, as you can see, there's like a whole bunch of stuff that comes with Anaconda that's geared towards machine learning and towards data science and data analysis type stuff. So the one that we're going to be using is Jupyter. Jupyter is the thing that comes with Anaconda that we're going to be using the most. So just, go to Anaconda, download it, comes with Jupyter. Once you have downloaded Jupyter, you can open up your little Anaconda Navigator. And your Anaconda Navigator looks like this. And you can launch a Jupyter Lab. Jupyter Labs are just very user-friendly, and they're what I suggest using. They're what I'm going to be using because they're just nice. They just make everything a little less stressful for people who don't know a lot of coding and aren't super familiar with like using terminal and stuff. I probably will be using terminal some. I use it every now and again to do some things when I need to, but for the most part we'll stick with Jupyter. Okay, so here's my Jupyter Lab window that I opened up, and let's see. Here is the first chapter of the book, essentially. This is the rough Jupyter Lab notebook form. It's also got a LaTeX file version that I've made and that I'm editing to use for, making it into a PDF and publishing it and everything. But this just goes through a lot of examples of linear algebra doing different things that are going to be super useful and absolutely 100% necessary for all of the quantum computing and quantum machine learning stuff that we're going to do. I really want to stress that too. So this isn't just a, hey, let's get you comfortable with linear algebra, never to see it again sort of thing. This is stuff that's going to get used over and over and over and over again throughout the entire book. And it's also stuff like if you actually really want to do any quantum computing or quantum machine learning or even just machine learning, this stuff is going to be really, really useful. So for the video, something really cool about Jupyter Notebook, that if you're not familiar with this, if you've never used it before, you can change the kind of cell to Markdown. And if you're not familiar with Markdown, it's just a really basic thing used for it's like a more basic version of HTML, basically. So like if you know what HTML is, Markdown's like a simpler version of HTML and can pretty easily be converted to HTML for web pages and things like that. And Jupyter will let you type in Markdown, which is great for math because you can enter in LaTeX code. If you don't know what LaTeX is a math scripting language that lets you make really pretty math stuff. So like, for example, let me find it. Yeah, so like things like this. Things like this with column vectors and row vectors and things. LaTeX lets you script up those things and make them look really nice. They're basically what every math paper and math book is written in, probably. So if you ever have written like a research article in math or physics, then you almost certainly used LaTeX to do it. And Jupyter lets you integrate LaTeX into Markdown cells. So if I wanted to, for example, create, so let's just create a title. To make the title, you just put a little pound sign in front of it. So let's do linear algebra video, shift enter, and that makes me a nice title. And then I change this next cell to math, and I can type things like mathy type things. So this will center everything into a certain little environment in LaTeX. Let's see, let's do P matrix like that, and this is going to spit out a column vector with 1, 2, and 3. See there? So LaTeX lets you do nice little things like that. You can script those up and make nice little math things. But then in Jupyter you can also do actual Python code. So this isn't just like a scripting thing, it's also for coding. And so in Python, and this is something I'm going to do a lot because so this lets you install software that we're going to be using a lot throughout the book. Pip install blah blah blah, pip install whatever is a thing that you usually run from terminal, but you can also run it from Jupyter Notebook. And if you're working in your Jupyter Notebook, that makes things a lot simpler. I've already run the pip install penny lane command in this notebook, and so I don't need to run it again over here. But just so you can see like what that does, I will run it again. And this is just going to install some software that we're going to need for quantum machine learning stuff. It's a really awesome free open source software, and I will show it to you guys in just a minute. And then a lot of the other stuff that we're going to need, so this imports the appropriate packages that we're going to need. Penny Lane is the quantum machine learning software that we're going to be using. It's open source. I'll show it to you in a few minutes. And then there's a wrapped version of NumPy in Penny Lane. And so rather than just doing like import NumPy as MP, which is like the typical thing that people do, you want to do the from Penny Lane import because the wrapped version makes it compatible with Penny Lane. It makes everything, I don't know, for lack of a better phrase, it makes everything quantum, whatever that means. So we're going to import these things here and run that. And once we have that, we can do some linear algebra in Python. So in Python, the typical way of making something like a vector or a matrix is by using array. And so you might say mp.array, and then you might enter, so for like a column vector, you might enter 1, 2, 3. Yeah, and this is gonna spit out a little column vector, or what you can think of as a column vector. It's basically this right here that we did in the LaTeX script earlier, right? But we're not actually going to use array. And this is going to be a little different from what most people do. Most people use array for literally everything. But what we're actually going to use is matrix. And although these two are almost always treated the same in Python, there is a function that allows you to take something called a Hermitian conjugate of a matrix or a vector. And you can't take a Hermitian conjugate of an array in Python. And so matrix is the preferred data type that we're going to use throughout. There may be cases where we need to define an array here and there for different things, but for the most part, everything's going to be a matrix. And something else, you can think of a column vector and a row vector as being special cases of matrices. So, for example, a column vector would just be a 3x1 matrix, right? It's got 3 rows and 1 column. And so you can think of column vectors as being like 3x1 matrices or n×1 matrices. And row vectors you can think of as being matrices as well, with 1 row and a bunch of columns. And so everything's going to be matrix because we're going to want to take Hermitian conjugates, which is the conjugate transpose of the matrix or vector. So like, let's just define a matrix. But for this matrix, I'm going to make it a column matrix, which is a column vector. And I'm going to put some complex numbers inside of it. And so if you don't know what complex numbers are, I'll talk a little bit about that in a second. But the reason that I want to do this is because I want to show you this function, this Hermitian conjugate function. So in Python, imaginary numbers, they use j instead of I. In most math texts, you'll see people will use I, but Python uses j for the imaginary numbers. So if you wanted to do like 3 minus 1j, let's see. And let's say, what do I want this entry to be? I don't know, negative 2j. Okay, so I've got a little column vector that I'm calling m, you can see here. Okay, and let's say I want to print m. So when I define m equals this matrix, up here I didn't do that. It's not going to print it out for me like it did up here. So I want to print it. That's super easy. Just tell it, print this thing. And you can see it prints the little 2x1 column vector or column matrix. And these are complex entries, right? So in typical math text, this will be 3 minus I and negative 2i, okay? But Python uses j. In the book, I'm going to use them interchangeably. I'm going to like go back and forth between the two notations depending on whether I'm typing things up in LaTeX and using, you know, mathy type language, or use j when I'm doing Python code. I make that very clear, and I talk about that a lot when I go through and, you know, explain what I'm doing. But yeah, just be clear that j is I is j. And in Python, if you're doing actual Python code, you have to use j. And you always have to have a coefficient, too. So if it's just 1j, you have to put the 1 there. Otherwise, it's like, I have no idea what you meant. And it gets confused. So always put a coefficient, even if it's just 1. And let's do the Hermitian conjugate of this column vector. Okay, so that's just m dot h. That's all you have to do, just dot h, and that does the Hermitian conjugate. And what does that give me? Oh, that gives me a row vector now. Okay, cool. So I have a row vector, and you can see the entries are different, but they're similar, right? So this first entry was 3 minus 1j. Okay, now this one's 3 plus 1j. So this is called the complex conjugate of this number. And all that means is you negate the imaginary part of the number. So I went from 3 minus 1j to 3 plus 1j. And now this one became plus 2j instead of minus 2j. And so that's the complex conjugate of the original negative 2j. So when I conjugate, I always make the imaginary part negative. Just negate it, and that's the complex conjugate. The real part of the number, the 3, stayed the same, right? So this dot h function, the Hermitian conjugate, it took the transpose of this, which means it just flips it along its diagonal and turns it from a column vector into a row vector. And it also conjugated all of the entries. And so let's see what that looks like with a bigger matrix. So for example, let's define a new matrix. And let's do like a 2 by 2 matrix now instead of just a column vector or a row vector. So let's do like negative 2j, 3, I need a comma there. And maybe down here, let's do 1 minus 3j and plus 4j. Okay, so that's my matrix. Let's print it so we can see it. Fun. Okay, so it's a 2 by 2 matrix, right? Nice little 2 by 2 matrix. And now let's do the Hermitian conjugate. Okay, so what this does is the diagonal entries here stay the same, and it flips everything along the diagonal. And that's what the transpose does. So you can see this 3 up here is now down here. Yeah, and the 1 minus 3j is now a 1 plus 3j up here in the right corner. So it flipped everything along the diagonal. And it also conjugated all the entries, right? So if we go through and you look, this was negative 2j, became plus 2j. This was plus 4j, it became minus 4j. And these two entries also got conjugated as well. And they got flipped, of course, from the transpose. So the dot h, the Hermitian conjugate, just takes the conjugate and the transpose of whatever matrix you give it. And this is going to be something that we're going to use a lot. It gets used a whole lot over and over and over again in quantum computing. So doing Hermitian conjugates is just like a standard thing that you do over and over and over again in quantum physics. And this has to do with operators. It has to do with, so like if you're computing things like expectation values or measurements or things like that, you might need to use a Hermitian conjugate. And this gets applied, generally speaking, to qubits, which I'll talk a little more about later in another video. And it gets also applied to the gates that get applied to the qubits in a quantum circuit. So if you want to understand quantum circuit diagrams, you want to understand how quantum circuit diagrams work, how these different quantum logic gates get applied to qubits, and what these diagrams mean. Hermitian conjugates of matrices are going to show up just over and over again. So it'll be good to understand those. I'll talk more about circuit diagrams in a later video, and I've already got a chapter written on circuit diagrams that goes through how to interpret all of these things. And so circuit diagrams are just linear algebra, like over and over again. Like really, if you want to understand quantum circuit diagrams like these, they're matrices applied to vectors. So it's lots of linear algebra being applied in quantum computing. So it's really important that you understand linear algebra, because if you want to read a quantum circuit diagram, it is linear algebra. Like you can see here, I've written out the linear algebra interpretation of this quantum circuit diagram. And explained exactly how to interpret this circuit diagram in terms of math. And so like quantum computing and quantum machine learning really is just like, I mean, it's really blurring the lines between math, quantum physics, and computer programming. You kind of have to be decent at all three if you want to do quantum computing or quantum machine learning. So it's kind of crucial that you understand the linear algebra and the other mathematics that comes into play. It's also kind of important to understand the quantum physics that happens in a quantum computer. It's also really important to develop some basic programming skills. So quantum machine learning is really blurring the lines between those things. So it's programming, it's math, it's quantum physics, all combined. And we'll talk more about that in a later video. I hope this was helpful. I hope this gets you somewhat started, and that some of this made sense to some of you, at least. And we'll jump into some more linear algebra in another video, and I'll talk about circuit diagrams and different things that'll be useful for doing quantum machine learning.